The other main thing we really need to look at is inequalities. I'm going to do it in two bits. The first bit is something we have seen before, the idea of looking at a graph to show an inequality. Not suggesting that we would solve this graphically, but of course it is possible to solve this graphically. So something like x squared on x plus 2 is less than or equal to 1. I mean, there's lots of different ways of solving these inequalities with pronumerals in the denominator, and we've seen a few. And one of them, as I say, was graphically. We could theoretically draw this graph up, but to draw x squared on x plus 2, I'm just going to work out where it's positive and where it's negative. So I've drawn the two graphs, x squared and also y equals x plus 2. I know there'll be a vertical asymptote there at negative 2. And breaking that into boundaries, I can work out where it's positive and negative. And I know there'll be an oblique asymptote if I do my division at x minus 2. So I can pop that in. And let's draw the graph. And then there's our graph. Now, depending on how accurate I've drawn that graph, and obviously this one's very accurate because I actually did it on a computer package, we could then solve the inequality of when is it less than or equal to 1, because I could draw in the horizontal line y equals 1 and simply have a look. Oh, where is that blue graph below 1? I've still got to find the points of intersection, however. As I say, this is an incredibly accurate graph, so I can read these ones off because it does turn out to be a whole number. But in reality, we probably would go and solve the equation x squared on x plus 2 is equal to 1. We get our two solutions. And so I now know the solution to the inequality was, well, this complete piece over here is below the red line, so x is less than negative 2, but also between these 2 points of intersection, it's below the red line. As I say, I'm not suggesting we would use that technique, but it is certainly a valid technique. This idea is probably more useful. Remember when we talked about inner rectangles and outer rectangles when we first looked at integration. But we know the actual integral is the exact area under the curve, and so it allows us to trap the area of the curve between two values. And often that's useful for solving some inequality. So, well, quite an old question now, but they told us to consider this graph, y equals the square root of x, and they gave us this sketch of the graph. And the first thing they wanted us to do, even though it's quite clear from the picture, but they wanted us to show that it's always increasing. So we use our first derivative for that, because remember, first derivative measures when the curve is increasing or decreasing. So our first derivative for this one is 1 on 2 root x. And sure enough, for greater than 0, that derivative will always be greater than 0. At the point x equals 0, y equals 0, I suppose it doesn't really matter because that's our starting point. All we're really saying is after the starting point, it's always increasing, and we have just proven that it is greater than 0 once we move off our starting point. So when x is greater than 0, y is greater than 0, but we know it's increasing. As I say, this last little bit I probably didn't need to do. The derivative would be sufficient. Okay. It then wants us to show that this particular sum is greater than or equal to the integral. And so that is the area of the outer rectangles. So again, there's our graph. So if I was to work out all these areas, this first one would be 1 times the square root of 1. The next one would be 1 times the square root of 2, and so on and so on. So it is in fact the same as the sum here they want us to look at. So as the square root of x is increasing, I know that the area of the outer rectangle will always end up being above the curve. And so we've got square root of 1 plus square root of 2 and so on will always be greater than the exact integral. They've also asked us to evaluate that integral. So let's add 1 to the power over the power, and subbing in we do get 2/3 n root n. Okay, so we've proven that little bit, or shown that a bit. Then the next bit was, like we looked at yesterday, an inequality induction. And now it's proving that that sum is less than something. So let's do that induction. Let's have a test for n is equal to 1. Left-hand side, square root of 1 is 1. Right-hand side, we get 7 on 6. And yes, 1 certainly is less than or equal to, but in this case less than 7 on 6. Hence, our result is true for n equals 1. We're going to assume the result is true for n equals k. K is some positive integer. So that's our assumption. We're now going to prove it's true for k plus 1. So that's what we're trying to prove. The sum of root 1, root 2, and so on up to k plus 1, always less than or equal to 4k plus 7 over 6 times the square root of k plus 1. Well, it is a series type, so I'll rewrite the left-hand side as the last term and the second last term, so I can say, oh yeah, look, there's my assumption, square root of 1 plus square root of 2 up to square root of k. We assumed that was less than or equal to 4k plus 3 on 6 root k. All right, we wanted, what was it, 4k plus 7 on 6, but it was times root k plus 1. So in this case, we haven't got a common factor. So, okay, I'm just going to write it all as one fraction then and see what happens. So over 6, but you'll notice the other thing I've done is I've turned the first one into an entire third. Okay, so I've got it as 4k plus 3 all squared now times k under the square root sign. And expand it out underneath that first square root sign. It factorizes to be k plus 1. Now, why did I try k plus 1? Because remember, we're trying to end up with root k plus 1 as a factor that I want to pull out. And so, sure enough, it is a factor almost, because you'll notice when I do my division, I have a remainder of minus 1. But that's okay, because we're dealing with an inequality here rather than an equality. So what I'm now saying is that line is basically what I want, minus 1. So it's smaller than what I want. So it's less than, I factorised the 4k plus 1 squared, but that's less than if I didn't have the minus 1. And so now I can factorise the root k plus 1, and we end up with 4k plus 1 lots of root k plus 1 plus 6, which is 4k plus 7, and that is indeed what we were trying to prove. Hence the result's true for n equals k plus 1 if it is true for n equals k. Oh, look, there's the old statement I used to write down. Very long-winded, but of course we don't write that down anymore. We just go, oh, well, it's true for biomathematical induction. Okay, it then asked us to use part B and part C to estimate what in fact the sum of the square root of 1 plus square root of 2 up to the square root of 10,000 would be to the nearest hundredth. We have now trapped the square root of 1 up to the square root of n between two algebraic expressions. Well, if I sub in 10,000, let's see what the left-hand side and the right-hand side end up being. And amazingly, to the nearest 100, because that's what we're trying to round off to, they are the same thing. So if I've trapped it between 600 and 66,700 on both sides, then that must be what it is to the nearest 100. We're now going to prove x is greater than sine x. X will always be greater than sine x for positive values of x. Okay. Here's my graph. Well, there's y equals x. There's sine x. And sure enough, it looks like x is always going to be bigger than sine x. But unfortunately saying, oh, it looks like it, is not good enough. Clearly at x equals 0, they are the same. If I have a look at the derivatives, so the slopes of those two curves, I don't know why I bother differentiating it, but obviously the slope of the line y equals x is 1. Sine x, it's differentiate that, we get cos x. But between 0 and pi on 2, so if I just look at this section here, between 0 and pi on 2, cos x will always be less than 1. So if the steepness of the the sine curve is always less than the steepness of the x curve, it must always be below y equals x, because y equals x is rising quicker. After pi on 2, it doesn't matter, because I know sine will now turn around and go back down, and pi on 2 is bigger than 1. So from that point on, then yes, it is going to be bigger. So y equals x increases faster than y equals sine x. So between 0 and pi on 2, yes, x is greater than sine x. Greater than pi on 2, well, we know sine x is always less than or equal to 1. So it is also x is greater than sine x. So combining the two ideas, we get x is greater than sine x. All right. In Patel, there's 10F's got some questions on inequalities and graphs. But again, as I've been saying with all the other ones, you've got the past papers and things like that. Yeah.